We know about metamorphic rocks from the previous lesson. These are rocks that have been altered by a number of geologic processes involving heat and/or pressure and/or the addition of fluids. In that lesson, I focused on foliated rocks, that is, rocks that have a distinctive lineation or pattern as part of their texture. In this lesson, I want to talk about non-foliated metamorphic rocks. These are metamorphic rocks that don't have a distinctive mineral orientation. Instead, minerals grow in equine shapes, that is, with equal dimensions in all directions. The reason that non-foliated metamorphic rocks are so interesting is because humans have spent a lot of time transforming them into objects of both value and beauty. The characteristics of non-foliated metamorphic rocks are determined by the protolith, the original rock chemistry prior to metamorphism, and the type of metamorphism that resulted in the non-foliated rock. Here are 3 common protoliths, 3 parent rocks, and 3 non-foliated metamorphic rocks that they turn into. Quartz sandstone, for instance, a typical beach sand, is metamorphosed to quartzite. Limestone is metamorphosed to marble. Basalts alter to serpentinite, and several other non-foliated metamorphic rocks that are used both in artwork and decorative stone. Some non-foliated metamorphic rocks, frequently those with sedimentary protolith, retain relic structures even after undergoing intense pressures and temperatures. Some non-foliated metamorphic rocks are specifically used as decorative stone because they have retained original sedimentary forms, structures, or even fossils. The state rock of Massachusetts, known as the Roxbury Pudding Stone, is an example of metasedimentary conglomerate, valued because it maintains the mixed lithologies of the original sediment. The Old South Church in Boston is made of it. All metamorphic rocks undergo changes in the solid state during metamorphism. With increased temperatures and pressures, minerals seek greater stability. As a result, crystal size will change, or the mineral type will change with no overall change in the rock chemistry, unless new chemicals are introduced by fluids. It is generally recognized that there are 6 ways that metamorphism occurs. It is important to remember that you cannot tell from the texture of non-foliated metamorphic rocks which type of metamorphism produced it. 3 of the metamorphic processes that result in non-foliated metamorphic rocks are characterized by an absence of dynamic stress. They are burial metamorphism, which is the result of loading and overlying material through sedimentary or tectonic processes. Heat is generated both by overlying pressure and the geothermal gradient, which is heat within the earth. Contact metamorphism results from heat produced by magma. The rock surrounding an intruding igneous body will be baked. In hydrothermal metamorphism, you have hot fluids associated with either an intrusive igneous body or a spreading center that alter the rock. But you can also get non-foliated metamorphic rocks in regional metamorphism. In that case, metamorphism results in the recrystallization of minerals into larger crystals. Both marble and quartzite can result from regional metamorphism. So let's take a look at some non-foliated metamorphic rocks. The first 2 I'll talk about are both beautiful to look at and are used as mineral resources. These are anthracite coal and banded iron formation. Anthracite coal provides a good opportunity to talk about the processes associated with metamorphism, even though coal has very little of a mineral component. Anthracite coal starts out as vegetation. If conditions are right and the organic matter doesn't decay, enough accumulated organic debris will first form peat, and then lignite, and then bituminous coal, and finally with heat and pressure, anthracite coal. During metamorphism, rocks frequently undergo dehydration and degassing, along with changes in mineral characteristics. With heat and pressure, the hydrogen and nitrogen organic compounds of lignite and bituminous coal break down, with the hydrogen and nitrogen escaping as gas. What results is the formation of pure carbon, or 90% carbon, which is anthracite coal. There's more that happens in the process. Sulfur is almost always found in association with large accumulations of organics. It's the result of bacteria. As the transformation from peat to bituminous coal occurs, sulfur crystallizes as pyrite, iron sulfide. In the metamorphic transformation to anthracite, the pyrite is broken down and the sulfur is released as a gas. The result of the metamorphism is that anthracite coal both burns with the most heat of any coal and produces the least sulfur residue. Sulfur, of course, is the pollutant that causes acid rain. Let's look at some anthracite coal. As a rock, anthracite coal preserves some original sedimentary features. It's glossy black and it has conchoidal fracture, which you can see here. Sometimes I'm lucky enough to generate conchoidal fracture with coal. Can you see it? In coal country, local artists do interesting things using anthracite as a sculpturing stone. Frequently, sculptors both pay homage to and poke fun at the coal industry. Banded iron formation is another non-foliated metamorphic rock that's a personal favorite of mine. Here are two samples. As the name implies, banded iron formation occurs as layers. The layers are predominantly chert, which is red, magnetite, which is gray, and hematite, which is a darker color. Depending on what exposure of banded iron formation you're looking at, there can also be other iron-rich minerals like goethite, which is used as a pigment and also known as brown iron ore. Frequently, the chert layers will have fine hematite grains in them, resulting in a spectacular red color. This variety of chert is called jasper. I think you can see it here. Banded iron in North America occurs in Michigan, Minnesota, and Wisconsin. At one time, up to 25% of the world's iron came from those states. It still remains an important source of iron ore, but banded iron also occurs in Labrador, Western Australia, Russia, Venezuela, Brazil, and in South Africa. As a result, the global market for iron is divided among those other producers. What's interesting about banded iron formation is the uniqueness of the material, the environment in which it formed, and the age of the world's banded iron formation. Most of the world's banded iron formation was deposited between 2.5 and 1.7 billion years ago. There's some banded iron that's both older and younger. So the origin of banded iron formation, or BIF as I lovingly refer to it in Minnesota, had something to do with global conditions. There had to be abundant iron, and there had to be very little oxygen, or the iron would have oxidized. In general, most geologists agree on the main components of the origin models of banded iron formation. BIF, as I mentioned, forms as sediment. Depending on conditions and depositional environments, the different sedimentary layers are deposited. If there is enough silica in the system, whether due to precipitation, volcanism, or terrestrial input, then chert is formed. If there is very little silica and very little oxygen, then magnetite forms. Finally, if there is a little silica but substantial amounts of oxygen, then hematite will form. In this way, banded iron records the development of oxygen in the Earth's atmosphere. So where do geologists disagree on the origin of BIF? The source of iron is a question. Is it eroded from land masses, or is it volcanically introduced to the sedimentary basins? What also is of interest is the exact mode of formation. There seems to be direct precipitation going on. There's also formation of oolites, indicating shallow currents being involved in the formation. Finally, there is also evidence of algal accretions. It's just really interesting stuff, and in addition to the economic benefits and the geologic complexity, it's fantastic stuff to look at. I take field trips up into the Upper Peninsula of Michigan with students. The geology is amazing up there. Exposed in these ancient rocks are glaciations, stromatolites, volcanic features, BIF, and a major mountain building event. It's a great place to visit. But there is an outcrop in Ishpeming, Michigan, that drives me crazy. It's called a couple of names, but Pilot Knob is one of them. And it has the most amazing exposures of deformed BIF, where the beds behave incredibly ductily. It's just amazing. But I always tell students to watch the path we take going up, because once on the knob, I have no idea which direction is which. The magnetite just plays havoc with my sense of direction, and I have a great sense of direction. So it's really disconcerting, and the students think it's funny as all get out. Other non-foliated metamorphic rocks are frequently used as building stone or decorative stone. It's a combination of both the rock hardness and the interesting growth of crystals that make these rock types both beautiful and functional. Serpentinite and hornfels are two examples of non-foliated metamorphic rocks that are used as decorative stone. Hornfels is a dark rock that is really fine-grained. It can look a little bit greasy. Almost any fine-grained rock can be metamorphosed into hornfels. Serpentinite is a metamorphosed igneous rock. From the basalt we have here, or a gabbro. It is usually a greenish color that can be either dull or glossy. Both serpentinite and hornfels show up as walls or steps in decorative settings. Quartzite is becoming more widely used for building and decorative stones. Quartzite is metamorphosed quartz sandstone. It is usually over 90% quartz, so it comes in very uniform colors. You recognize the difference between quartzite and quartz sandstone by carefully looking at the makeup of the rock. Quartz sandstones are made up of sedimentary grains that will have rounded edges and pores. During metamorphism, those quartz grains in the solid state recrystallize and grow. In that process, individual quartz crystals interlock and develop flat edges rather than the rounded edges of the grains that make up quartz sandstone. It's the interlocking larger crystals that give quartzite both its strength and its beauty. Quartzite in the United States has been used not just for decorative stone, but for construction as well. The consistent nature of the quartzite allows it to be cut as bricks or blocks for buildings. In the upper Midwest, the Sioux quartzite has a distinctive red, and it's incredibly hard. It has been used for constructing buildings for over a century that, of course, have a distinctive red color. The David Whitney House in Detroit, built in 1894, is Sioux quartzite, as well as the Fowler Methodist Episcopal Church in Minneapolis. Sioux Falls, South Dakota is known as America's pinkest city because so many buildings are built out of Sioux quartzite. In the east, a distinctive component of the Appalachian Mountain Belt is the Blue Ridge. It's a quartzite with low-grade metamorphism, meaning the original sandstone wasn't altered all that much. Nonetheless, you do have crystallized quartz-rich stone that is frequently used for construction. The Graham County Courthouse in western North Carolina is an example of a building built with Blue Ridge quartzite. Where quartzite has seen its real boom is in use in countertops. In addition to being a very durable stone, quartzite resists staining. Of course, characteristics vary with specific quartzite, but the selling point is that quartzite is harder than granite and resists stains better than marble. The color can be attractive as well. Quartzite stone countertops are very different from countertops that are made when manufacturers mix sand grains with epoxy. These are often called quartz countertops or engineered stone countertops. These are synthetic countertops made from around 90% quartz sand grains and then a blend of resins and polymers to make it into a stone-like product. The technology was developed in Italy, but there are several US makers. In addition to being a durable and non-porous countertop, these products can be stained or flecked in a very consistent pattern, an important aesthetic selling point. The one drawback is that the resin component of the rock makes it less heat resistant than most natural stone countertops. The last group of non-foliated metamorphic rocks I'll talk about are those that have been used for artistic purposes as well as construction and decorative stone. Examples of these are soapstone, marble, and a particular favorite of mine, pipestone. Soapstone is one of these rocks that has been used by humans for thousands and thousands of years. In fact, people would go out of their way to find locations where soapstone could be mined. The soapstone in this discussion is non-foliated and formed by hydrothermal alteration. But I do want to point out that there is another soapstone formed by dynamic metamorphism that is foliated. Moreover, both types have the same protolith, which is either a basalt or its coarser-grained cousin, gabbro. All soapstone has abundant talc, which is what makes it soft, although hardness can vary. All soapstones also have varying amounts of mica, chlorite, amphibole, quartz, and magnesite. As a result of varying composition, soapstone comes in different colors. When it's green or brown, soapstone is simply called soapstone. When it is black, it is referred to as steatite. The reason soapstone has been carved for thousands of years is because the talc component makes it a very soft rock. Soapstone can be up to 90% talc. Frequently, you can carve it just with a fingernail. It has a soapy feel, and as you can see from this carving, it also gets damaged easily. Soapstone has been used in a number of different ways. It was frequently used to make molds to cast metal in. Early ironworkers would pour molten iron into sculpted shapes in a soapstone. During the Revolutionary War, soapstone was used to cast lead bullets. In more recent times, soapstone has found increasing use as dimension stone and is noted for unique thermal properties. High school laboratories frequently have soapstone counters because soapstone isn't damaged by heat or acid. Wood stoves made of soapstone can be both spectacularly ornamental and thermally efficient. It absorbs heat slowly and then radiates it for hours. The same effect works with cooling as well. I have these soapstone cubes that you put in the freezer. They cool down slowly, but stay cool for a long period of time. So if you like to drink something but don't want to dilute it with melting ice cubes, this is the way to go. Soapstone is also used as an insulator because it doesn't conduct electricity. It's also being increasingly used for decorative stone on walls and counters. It makes a great backsplash in ornate bathrooms, fantastic colors, and waterproof. It is the carving of soapstone that really stands out as its most recognizable use. The artistic work generated by indigenous sculptors in North America, South America, Australia, and elsewhere were part of daily functional life, religious worship, and artistic creativity. Examples of soapstone carvings can be found in many museums. One of my favorite sculptures that uses soapstone is the famous Christ figure on the summit of Mount Corcovado in Rio de Janeiro. The structure of the sculpture is cement, but the surface finish is a soapstone that is mined in Minas Gerais, Brazil. And here's a sample of it. Of course, marble is also famous for its use as a medium for sculpture. In addition to being relatively soft, marble has a translucent quality that when polished gives the sculpture a lifelike quality. If polished correctly, a marble figure of a human can be spectacularly realistic. Two of my favorite sculptures are Michelangelo's The Slaves at the Louvre Museum in Paris. Sculpted out of Carrara marble, which is quarried in the Apennine Mountains of Italy, the flesh of the individuals depicted in the sculpture is remarkably lifelike. You could almost forget they were stone. Except Michelangelo left some unfinished stone as an integral part of the sculpture. The effect of the polish and texture is mind-boggling. Marble also has been used as building stone for a very long time, including the Parthenon of Athens, where a limestone foundation was built with a superstructure of marble. A more recent example is the Taj Mahal, built in the 1600s. The Taj Mahal is famous for its beautiful marble edifice. In the US, we frequently use marble for building stone. The Supreme Court building in Washington, D.C. is a spectacular marble building that used marble from Vermont, Georgia, and Alabama. Using different types of marble on the same building is in fact common. Marble comes in different shades and colors depending on secondary minerals. Marble is a predominantly calcite and it's formed from the metamorphism of limestone. Limestones frequently have interbedded units or will incorporate organic dyes. The result is different color marbles with different characteristics. The Lincoln Memorial has an edifice of white gray marble from Colorado, but the floor is a pink marble from Tennessee. The statue of Lincoln himself is made from a very white marble from Georgia. Each of those stones and the other stones used in the construction of the monument, which includes a granite and a limestone, were chosen because of the aesthetic characteristics. By contrast, the Washington Monument was made of different marble because of supply problems. The base of the monument is made of a marble quarried in Maryland in the mid-1800s. But because of the lack of funds to complete the monument, construction was stopped for 30 years. When architects went back to that same marble quarry, the marble was no longer available. So a similar marble from another Maryland quarry and several Massachusetts quarries were used. You can see the differences in the stone if you know the history of this great structure. Exceptionally white marbles are very rare and highly valued. I teach classes in northern Italy near where Lassa marble is quarried. Here's a sample. After World War II, the U.S. took part ownership of a quarry at that site and used the marble for military headstones. A second quarry in the same marble was the source of the marble for the Ground Zero Oculus built in New York City. It's spectacular stuff. Much of it is pure white. Uniquely, that marble went through 2 regional metamorphic events, so it's a little bit harder and makes a great dimension stone, as well as an ornamental stone. I want to take a minute to point out that not every dimension stone or countertop that is called a marble is actually a marble. This is similar to the point I made about the term granite being extended to rocks that were not granite. Marble is a rock that has undergone a metamorphic change. There are many limestones that are resistant to wear, beautiful to look at, and good for building. But if they are not metamorphosed, they are not marble. This plate is an example of the Devonian fossil limestone of Morocco. There are spectacular marbles in Morocco that have been quarried since ancient Roman times. But this is a dark rock that contains fossils, and it's sold as a marble for countertops and tables. It's a limestone that when polished is very hard, but still, it's not a marble. Here's a bowl I bought on the Istrian Peninsula. This is frequently called a marble, but it is Istrian stone from the Jurassic period that is widely used in Venice. This is an impermeable limestone that is used in the lower floors of Venetian buildings because it keeps the water out. Used from the 16th to the 18th centuries, it was expensive to mine and ship from what is now Croatia because of its beauty and its strength. It is not a marble, but it is marvelous stuff. So when you are paying for marble, make sure you are getting marble. Most marble mines are very well known and well studied. You should be able to find out a lot about the geology of your countertop. The last non-foliated metamorphic rock I'll talk about is a personal favorite. It's the Pipestone exposed at Pipestone National Monument in southwestern Minnesota. I bring students there every year. It's a location that has great outcrops of Sioux quartzite and active pipestone quarries. In addition, the Visitors Center at the monument has Native American artists there to explain and demonstrate the carving of pipestone. Pipestone is even softer than marble and many soapstones. This particular pipestone is also known as catlinite. It's made of soft, clay-sized crystals, too small to see. Although it occurs interbedded with the Sioux quartzite, there's almost no quartz within the pipestone. Traces of hematite give the pipestone its unique red color. Pipestone has long been carved into peace pipes, both because it was easily carved and because of the red color. It became an important part of Native American traditions and religion. It was considered so valuable that pipestone quarries were regarded as sacred ground. For that reason, members of any tribe could travel freely to and from the pipestone quarries without being harassed by warring tribe members. Of course, signing over the quarries to the federal government was the source of great angst for Native Americans. However, the Park Service has done a very good job in both protecting the site and providing access for present-day Native quarriers. If you go there, you can see how the pipestone is carved. There are amazing pipes and sculptures on display. So that's how rocks become integral to art. From earliest times, people recognized both the beauty and the characteristics of these rocks that allow artistic augmentation. Marble, soapstone, pipestone, geologically, they're all non-foliated metamorphic rocks. It's really great stuff.